Blade shape determined who walked away from a fight and who didn't. Here's why each design existed. Every curve, taper, and edge solved a specific problem in combat. From single-edged efficiency to specialized contours, each sword blade shape carries hidden advantages forged through centuries of warfare. Let's break down exactly what made each one work. Single edge. Single-edged blades dominated battlefields across cultures for one reason: structural efficiency. By concentrating steel thickness along the spine, these blades achieved superior strength without added weight. The thick back prevented bending during forceful cuts, while the single edge reduced manufacturing cost and time. This design allowed soldiers to place their hand on the spine for additional control during thrusts, a technique impossible with double-edged weapons. In military context where thousands of weapons were needed quickly, this advantage was decisive. The design also created a natural weight distribution that enhanced cutting power, making single-edged swords like the katana and backsword devastatingly effective against unarmored opponents. Double edge. Double-edged blades offered a different advantage: versatility in combat. With cutting edges on both sides, these weapons eliminated the need to orient the blade during rapid exchanges. A fighter could cut with either edge depending on the angle of attack, making techniques faster and more fluid. Double-edged designs like the arming sword and longsword allowed both forehand and backhand cuts with equal effectiveness. The symmetrical design also created superior balance, with the center of percussion aligned perfectly with the grip. In thrusting attacks, double edges could slip between armor plates from any angle. The trade-off was reduced structural strength compared to single-edged equivalents, but for warriors who valued adaptability over raw cutting power, double edges were the superior choice. Curvature and overall profiles. Straight blades excel at one thing: thrusting penetration. The linear geometry allows force to transfer directly along the blade's axis, driving the point through armor gaps, mail rings, and flesh with maximum efficiency. Straight designs like the Roman gladius and rapier could reach vital organs with precision that curved blades couldn't match. In formation fighting where soldiers stood shoulder to shoulder, straight blades could thrust between shields without the wielder exposing themselves. The geometry created predictable handling characteristics, making straight swords easier to master for common soldiers with limited training time. Curved blades revolutionized cutting efficiency through geometry. When a curved edge contacts a target, it creates a slicing motion rather than a pure chop, dramatically reducing the force needed to cut through flesh and bone. This principle made curved swords like the saber and scimitar dominant cavalry weapons. A rider's forward momentum combined with the blade's curve to deliver devastating cuts as they passed opponents. On foot, curved blades allowed draw cuts, where the wielder pulled the blade across the target while cutting, multiplying effectiveness. The design required less physical strength to inflict serious wounds, making curved swords accessible to fighters of varying builds.
Recurved swords are characterized by an S-shaped edge, like falcata, kopis, or kukri, that typically curves forward, concave near the hilt, and then back, convex, toward the tip. This design combines the chopping power of an axe with the long cutting edge of a sword, shifting the strike point forward to increase leverage and lethality. Advantages of the recurve design. Kinetic impact. The forward tilt places more mass at the point of impact, delivering a blow with the momentum of an axe. Efficiency. The S-curve allows for a continuous slicing motion as the blade travels through a target, even after an initial heavy impact. Stabilization. Many recurved swords, like the falcata, feature a hooked hilt that prevents the blade from slipping from the wielder's hand during high-momentum strikes. Short inward curved, like the fall, a Thracian or Dacia hook-bladed weapon. The short falx was highly maneuverable, making it ideal for close-quarters combat while simultaneously carrying a shield. Tactical advantage. Its inward curve allowed warriors to hook the blade over the top of an enemy's shield to strike at the head, neck, or limbs. Forward curved blade like kopis, falcata, or yatahan, they have extreme chopping power. By shifting the blade's center of mass forward, these swords concentrate energy toward the tip. This creates a long-bladed axe effect, delivering devastating blows that can split shields or crush helmets. Back-curved tip blades with back-curved tips, like certain Chinese Dao variations, combine straight blade thrusting capability with enhanced tip cutting power. The curve appeared only in the final portion of the blade, creating a hooked tip that could slash effectively while maintaining a straight profile for most of its length. This design allowed the weapon to function as both a thrusting and cutting tool without the handling compromises of fully curved blades. Width, taper, and contour. Leaf-shaped blade. Leaf-shaped blades widen in the middle third before tapering toward the tip, creating a profile that resembles a leaf. This geometry solved a critical problem:
how to maximize cutting power while maintaining a short, penetrating point. The widened middle section increased mass at the optimal striking zone, delivering devastating cuts, while the tapered tip could still thrust effectively. Ancient Greek Xephos swords used this design to excel in both slashing and stabbing. Flared tip blade. Flared tip blades feature visible widening near the point, concentrating weight exactly where it delivers maximum impact. This design turned the tip into a devastating cutting tool rather than just a thrusting point. The flare increased the moment of inertia, making tip cuts significantly more powerful than parallel-sided equivalents. Nepalese Kora sword demonstrated this principle with flared tips that could deliver crushing blows capable of breaking bones through armor.
Tapered blade. Tapered blades feature continuous reduction in thickness and width from hilt to tip, like stock or oakshot Type 15, medieval arming sword. This geometry created the fastest, most responsive handling characteristics possible. By removing unnecessary weight from the blade's forward section, tapered designs like the rapier achieved lightning-quick point control. The taper also concentrated flexibility toward the tip, allowing the blade to bend slightly during thrusts, absorbing impact shock that would break rigid blades. Parallel-sided blade. Parallel-sided blades maintain nearly uniform width along their length, with minimal tapering. This design prioritized durability and consistent cutting power across the entire edge. Military swords like the Roman gladius used parallel sides because they could withstand repeated impacts without weakening. The uniform width also simplified manufacturing and blade maintenance, as any section of the edge could be resharpened to the same profile. Broad blade. Broad blades feature wide profiles designed for devastating cutting power. The increased width created greater mass behind each cut, delivering wounds that incapacitated opponents immediately. Scottish basket-hilted broadswords exemplified this principle, with wide blades that could break bones and sever limbs. The broad profile also increased the blade's moment of inertia, making it harder for opponents to deflect or parry. Narrow blade. Narrow blades sacrificed cutting power for speed and thrusting efficiency. The reduced width decreased weight dramatically, allowing for rapid attacks and superior point control. Small swords took this principle to its extreme, with blades so narrow they were nearly triangular in cross-section. This made them the fastest swords in existence, capable of delivering multiple thrusts before heavier weapons completed a single action. Blades with special contours. Wavy-bladed sword. Wavy-bladed swords like the Moro Chris sword feature undulating edges that create a flame-like appearance. The waves served a practical purpose. They increased the effective cutting edge length within a given blade size. Each wave created additional cutting surface, making wounds more severe than straight-edged equivalents. Some Flamberge greatswords used wavy blades, though their primary advantage remained the increased edge length. Sickle sword. Sickle swords feature pronounced curvature that creates a hooked, sickle-like profile. This extreme curve concentrated all cutting force at the blade's belly, creating devastating chopping power. The hook also allowed pulling cuts, where the wielder could hook an opponent's limb or neck and pull the blade through the target. Egyptian Hopesh swords demonstrated this principle, functioning as both sword and hooking weapon.
Flexible whip swords feature segmented or extremely thin construction that allows the blade to flex like a whip. The Indian Urumi exemplifies this design with multiple thin blades that could wrap around shields and strike from unexpected angles. The flexibility made these weapons nearly impossible to block with conventional techniques. However, they required extensive training to avoid injuring the wielder, making them weapons of specialized martial artists. Semi-flexible blade features moderate flexibility that absorbs impact shock without compromising structural integrity. This design prevented blades from shattering when striking hard targets like armor or bone. The flexibility also allowed the blade to bend slightly during powerful cuts, storing and releasing energy that increased cutting power. Many European longswords featured semi-flexible construction, allowing them to survive the brutal impacts of armored combat. Rigid reinforced blade prioritize absolute stiffness through thick spines or specialized construction. This design prevented any bending during thrusts, allowing maximum force transfer into the target. Estocks and other armor-piercing swords used rigid construction because flexibility would dissipate the force needed to punch through plate armor. The reinforced spine also prevented the blade from twisting during powerful cuts. Hook blade swords feature curved blades ending in sharp hooks, with the Chinese hook sword being the primary example. The hook could catch and control an opponent's weapon or limbs, creating openings for counterattacks. When used in pairs, hook swords could be linked together, extending reach, or creating a double-bladed weapon. Serrated or sawback swords feature teeth along the spine, with the Russian M1827, British 1856, and Swiss M1842 being pioneer examples. The serrations served as utility tools for cutting rope, wood, or other materials, making these swords multi-purpose implements for soldiers in the field. The teeth did not enhance combat effectiveness, but they added practical value for military campaigns. Broad and flat blade, exemplified by the executioner's sword, feature wide, flat profiles designed for specific purposes. The executioner's sword used this geometry to deliver clean, decisive cuts for beheading. The wide blade provided weight and stability, ensuring the executioner could deliver a single, humane blow. The flat profile prevented the blade from twisting during the cut, maintaining proper edge alignment. If you want more detailed breakdowns of sword design, subscribe to Swords Explained. Every blade shape tells a story of human ingenuity under pressure, and understanding these advantages reveals why certain designs dominated their eras while others faded into history.